Okay, so let's look at 15.4. So a curve C parameterized by R of t is simple when it does not cross itself. So for example, this figure 8 over here would not be simple because it crosses itself right here. But this guy down here would be simple because it does not cross itself. Okay, a connected region R is called simply connected when every simple closed curve in R encloses only points in R. So for example, I guess if I say close this guy here, that would be simply connected, this guy here. So informally, a simply connected region has no holes. Okay, so now let's look at Green's theorem. That's what this section's about. So Green's theorem says the following. So let R be a simply connected region with smooth boundary C oriented counterclockwise. If F equals Mi and J, so that's our vector field, so it's just in 2 dimensions, and I and J, there's no K component here. And if they M and N have continuous first partial derivatives in R, then this is true down here. So the line integral over the boundary of F equals the double integral over the region, simply connected region, of N derivative with respect to X minus M derivative with respect to Y dA. We're not going to prove this, but in 15.8 we will prove a special case of Stokes' theorem, and this follows from Stokes' theorem. So Stokes' theorem is a more generalized version of Green's theorem. So pretty much Stokes' theorem will be pretty much Green's theorem in 3 dimensions. So here we have an I and J, there's no K component. For Stokes' theorem we will have a K component. So Stokes' theorem is a generalization of Green's theorem, which it will prove a special case of later. Okay, so now let's look at an example using Green's theorem. Okay, so let's look at an example. This is from practice quiz 8, number 3. It says verify Green's theorem over the triangular region that has vertices at 1, 1, 3, 2, and 4, 5 when f is equal to x plus y I direction plus 2x y j direction. So this would be your m, the x plus y, this would be your n, the 2x y. So I've graphed these 3 points. It's a triangular region here. So here's Green's theorem. So again, it's relating a line integral around the boundary to a double integral over the region. So the region here would be inside the circle, and the boundary would just be on the outside of the, the region would be the inside of the triangle, and the boundary would be going around the boundary of the triangle here. And by Green's theorem, the C has to be taken counterclockwise. So you can see I'm going counterclockwise. I got C1, C2, and C3. Okay, so let's do, so basically to verify we have to show this side equals this side. So let's first do the line integral side. So to do that we're going to have to parameterize C1, C2, and C3. So let's do that. Okay, so parameterize our C1, so let's call it R1. So we're starting at 1, 1. So we're calling it a parameterized line, your start point plus the end point minus the start point times t. So simplifying this, we'll have 1 here plus, that'll be 3 minus 1, so plus 2t. And here we'd have 1 plus t. We could write that then as 1 plus 2t I plus 1 plus t j. And when you parameterize a line, the t always goes from 0 to 1. Okay, let's parameterize C2 next. So let R2 be the parameterization of C2. There's going to be our start point, which is 3,2, plus our end point, 4,5, minus our start point, 3,2, t. So let you check then, if you work this out, you'll get 3 plus t I direction plus 2 plus 3t j direction. And again, t goes from 0 to 1 in this. Now let's do parameterize C3, let's call it R3. So let's do that. So now I'm parameterizing C3, so our start point is 4, 5, so I have it here. Then plus endpoint 1, 1, subtract start point 4, 5 times t. So let you check then, it becomes 4 minus 3ti plus 5 minus 4t. Okay, so let's keep going. So let's find the derivative. So R1 prime. So looking at it over here, derivative with respect to t, as it is 2i. Derivative with respect to t would be 1, so it'd just be j. That's that one. And say R2 prime. So derivative of this guy with respect to t would just be 1, so it'd be just an I there. And derivative of this guy with respect to t would be 3j. And lastly, R3 prime, so it would be minus 3i minus 4j. Okay, so now let's start doing the line integrals. Let me erase some things here. So let's do the integral over C1. So here's my R1, and here's my R1 prime. So by definition, the line integral will be, well, these guys again will go from 0 to 1 on our t, so it'll be 0 to 1, f of R1 dotted with R1 prime. Okay, so this is my x then here, and up here y, and here's a function over here, it's x plus yi plus 2x yj. So it has to become integral 0 to 1. It's going to be x plus y, so it'll be 1 plus 2t plus 1 plus t, that would be I, plus 2 times x, which is 1 plus 2t times y, is 1 plus t j. This thing dotted with 2y plus j, then dt. Okay, so let's work this out. So adding things here, so 2t plus t would be 3t, 1, 1 is 2. Then multiplying this stuff out here, you'll get this right here. Then doing a dot product now, we'll get then, so doing a dot product, we'll have 2 times this guy, so I have 2 there, and 1 times this will be this guy here. Then combining stuff here, so it'll be then 6t plus 4 plus 4t squared plus 6t plus 2 dt. This becomes then integral 0 to 1 will be 4t squared plus 12t plus 6. So I'm going to integrate this now. So it'll be then 4t cubed over 3 plus, will be t squared over 2 is going to be just then 6t squared here plus 6t evaluated at 0 and 1. So working this out, be 4 thirds, be put a 1 here and here, it'd be plus 12 Let's leave it like that for now. Okay, now let's do C2 next. Okay, let's do our C2 guy now. So here's my R2 and R2 prime. So here's the definition of line integral here. Again, 0 to 1 because we parameterize a line. So here's my x and y. So it's going to be then integral 0 to 1. It's going to be x plus y, so adding those two. So it'll be 3 plus t plus 2 plus 3t. That's in I direction. Plus 2 times x, 3 plus t times y, 2 plus 3t, j direction. This guy is dotted with, let me put the dot here I guess, I got a space, dotted with I plus 3j dt. Okay, so let's do that. Okay, so simplifying, you have a t and 3t would be 4t, 3 and 2 is 5. And multiplying this stuff out, let you check, it's 6t squared plus 22t plus 12. Now we'll do the dot product. So let's do dot product. So doing a dot product, so it'll be I times I, it'll be 4t plus 5, and then j, 3 times this guy, the j component, 3 in front here. Then combining like terms, I'll let you check then, let's combine like terms here. So combining like terms, you have an 18t squared and a 66t plus another 4t, so 70t. You have a 36 and a 5, so 41. So now let's integrate this. So integrating with 18t cubed over 3 plus 70t squared over 2 plus 41t. The average reduces to 6t cubed plus 35t squared plus 41t. Putting 1 and 0 in, you should get 82. Okay, so we've done C2 now. Now let's do our last one, C3. Okay, now let's do integral over C3. So here's my R3 and R3 prime. So here's our definition. And this is what I put in place of x in my f function over here, and what I place in place of y. So we get this. Then when you dot that, you get this. You can work it out here. And then you get this down to here, 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 and here. So this should be the answer you get for this line integral. It's negative 169 over 2. Okay, so let's put all three together now. So putting all three results together, we have then, it should be C3 here. So the integral over C would be integral over C1 plus integral over C2 plus integral over C3. So let's add the three answers we got. So the C1 guy was 4/3 plus 12. The C2 guy was 12. And the C3 guy was 169 over 2. So when you combine those, you get 65 over 6. So this is the left side of Green's theorem. Now we still need to do the double integral over R. So here's Green's theorem again. So we've done this side, we've shown it's 65 over 6. So this double integral should also be 65 over 6. So let's work on this double integral now. Okay, so now we have to do the double integral over the region R. The region R was a nasty triangle. We could do it, but it'd be kind of a pain to, you have to do a double, two integrals probably to integrate over it. Instead, let's use change of variables and change it into a right triangle with one of the vertices 0, 0, 1, 1, 0, 1, 0, 1. So in particular, let's send my this guy to that one. So it'd be t of 0, 0, it goes to 1, 1. Let's send this one, so that would be 0, 1. Let's send that to 4, 5. And let's send 1, 0 to 3, 2 over here. So that's fine. So here's my affine transformation. So it's always the case you can map any triangle into a nice right triangle like this. So let's find conditions on A, B, C, D, E, and F that make this true. So let's look at this first guy. So 1, 1 equals t of 0, 0, that's what we want. So that means you put 0 in place of u, so here, and 0 in place of v here, here, and here. So when you do that, putting 0 here and here, just have a c left on this guy, and putting 0 here for u and 0 for v, you have an f. So it looks like then c equals 1 and f equals 1. So we could take the c away now here and put a 1 there. We could take the f away and put a 1. So we've done that one. Let's move on to this one next. So next looking at, we have 4, 5 equals t of 0, 1, that's what we want. So it'd be 0 for u, 1 for v. So putting 0 u here would be gone. 1 for v it'd be b plus 1. And 0 for u, 1 for v, e plus 1. So that is equal 4, 5. So you have then b plus 1 equals 4 and e plus 1 equals 5. That implies then, this would mean that b is 3. And this guy, when subtracting 1, e is 4. Okay. So now let's replace the b up here with 3 and replace the e with 4. Okay, we still have to find a and d now. Let's use, so we've done that one, let's use this guy now to find the a and d. Okay, so doing the last one, so 3, 2 equals t, 1, 0, so put 1 in place of u, 0 in place of v, you'll get a plus 1, comma, d plus 1. That is, a plus 1 has equal 3, d plus 1 has equal 2, solving, get a is 2, d is 1, so a is 2 and d is 1. Okay, so now let's find the Jacobian of this mapping, so let me erase a few things. So here's my Jacobian definition, so this is my x up here, my y over here. So derivative of x with respect to u would be 2, derivative of x with respect to v would be 3, derivative of y with respect to u would be 1, derivative of y with respect to v would be 4. So working this out, it'll be 8 minus 3, so 5. Okay, so now let's do the change of variable formula. Okay, so summarizing, we have it here. Here's our f, this is the t we found, this is the Jacobian we found. So we have to find this double integral now. So the n is the 2xy guy. So derivative with respect to x of this guy would be 2y. And my, here's my m, so derivative with respect to y would just be 1, so it's minus, so it'll be minus 1 here. Don't have our dA. Now we're going to change variables, so we're going to use the change of variables formula. So using a change of variables, this double integral over r, this should be double integral, should equal the double integral over s. So we're going to replace the y now with this guy up here. So it'll be u plus 4v plus 1, so that's what I did here. Then subtract 1 times our Jacobian, which is 5. I'm going to go dv du. That means I'm going to be looking at strips. Here's my s over here. I'm looking at strips going this way. So we need to write v as a function of u, so that you check if you find the equation of this line here. It's v equals negative u plus 1. So let's now figure out the limits on s. So limits then would be, well, the strip goes from 0 to up here, which we're calling negative u plus 1. Then the u gets the range between 0 and 1, so we got this over here. I pulled a 5 outside the integral, then multiply this out and simplify it, I got to here. Okay, so let's keep going now. We need to integrate with respect to v. So integrating, I get this, so integrating 2u would be 2uv, integrating 8v would be 4v squared, integrating 1v. Now I'm going to put the negative u plus 1, sorry, in place of v here, here, and here. So making a substitution, we get this. Now we could just expand this, but I'm actually going to do a w substitution. I think it might save a bit of time. So I'm letting w equal negative u plus 1, then dw du would be minus 1, so du would be negative dw, and solving for u, because I'm going to have to replace the u over here, I get u equals 1 minus w. So let's make the substitution now. So making a substitution, I get this. So w1 then, so putting 1 here would be 0. w0 would be 1. I can then switch this integral around, and let me just write another step here. I just noticed I made a mistake here. I forgot to bring this 2 over, and I forgot a w here, so this guy should have been like this. Okay, so then multiplying this inside out, it should be 2 here actually, also. I get this, and let's combine like terms. So I combine like terms, I got 2w squared because you got a 4w squared minus 2w squared, and 2w plus w is 3w. So integrating, we get 2w cubed over 3 plus 3w squared over 2, and 5 in front still, 1 to 0. Okay, so then plugging in 1, we get 5 times 2/3 plus 3/2, which can be written as 5 times 4 plus 9 over 6. It's 11, so 11 times 5, sorry, 13 times 5 is 65 over 6. And that's the same answer we got doing the line integrals. So we verified Green's theorem. We show the line integral side equals the double integral side. So we're done.